afternoon and welcome to the February meeting of the Astronomy Club of Akron. Today it's our good fortune to have as our guest speaker Mr. Gary Kader from Baldwin, Wallace University. Thank you for coming and visiting with us, Mr. Kader.
Okay.
He's the observatory director of the Burrell Observatory at Baldwin Wallace. And if you've not seen a picture of the observatory, it is absolutely beyond description. It's classic architecture of perhaps, 100 years ago, maybe?
Oh, no, 1940.
1940.
Right out of central casting, though. Okay, when you think about it, okay?
So, anyway, thank you for your welcoming. And Mr. Kader, I'll give you the floor.
Okay. Well, I'm going to talk to you about the HR diagram, which you probably are all somewhat familiar with, but hopefully I add enough to it so that you'll learn something. All right. So, but I will start out with a lot of basics because I'm going to guess we have a mixture of people that are just somewhat familiar with astronomy and some people that are very familiar and some people are just getting started. So we'll try to bring everybody up to date if we can. This is a plot of luminosity versus temperature, okay? And it was created independently. Oops, what happened there? Okay, it was created independently by Hertzsprung in 1911 and by Henry Norris Russell. Hertzsprung was a Danish astronomer. Russell was a U.S. astronomer, and they did it independently, and that's why it has the two names. They didn't collaborate on it. So let's talk about luminosity versus brightness. Okay, we use these terms in our everyday vernacular kind of interchangeably, and luminosity has to do with how much light a star is giving off. Think about it. I don't know why this thing keeps fading out.
Want to use the headset?
No, it's all right. Yeah, why don't I do that? This thing keeps fading out on me. Let's turn this down.
Well, we also have this one, Gary, if you'd like to use it. We have one that has a wire to it. If you want to use
No, that's okay.
That one doesn't fade out. But
Oh, cool. Now I feel like a carnival barker.
if you have a wire, come behind it.
Oh, okay. All right.
Hold the mic right up to your mouth.
Okay, does that work?
And that one's
There we go. Turning it on probably goes. Okay. Yay, okay, that works. All right. So, brightness is how bright a star appears to us. It's magnitude, Joe. Magnitude system, right? Luminosity has to do with how much energy it's actually giving off, how bright a star actually is. Think of it as the wattage on a light bulb, okay? And how bright a light bulb appears to you depends really on, its luminosity and how close it is to you. So, brightness is inversely proportional. It's directly proportional to the luminosity. Okay, whether you got a 100-watt light bulb or a 25-watt light bulb, okay? And it's inversely proportional to the distance squared. So this is what you're looking at here. So with brightness and luminosity, where's my pointer here? I guess this will work. There you go. All right. From brightness and luminosity, you can figure out a distance. Okay? So those are the three variables. And from the distance and the brightness, you can figure out the luminosity. So if you know two out of the three, you can figure out the third one. And the most luminous stars are about 1,000,000 times more luminous than the sun. And the least luminous stars are about 1/10,000th. So the sun is, as you'll see, is kind of a average, a little bit below average star. And so, as I said, if we know the luminosity and the brightness, we can figure out the distance. So absolute magnitude is another way to figure out, in order to talk about brightness. Now, usually luminosity, rather. Luminosity is usually given in solar luminosities or total wattage. But absolute magnitude is another way, and it turns out that absolute magnitude is a way to, if you use that, you can actually figure out its distance a lot easier. Absolute magnitude is how bright a star would be if it was 10 parsecs away. A parsec is how far a star would have to be to have 1 arcsecond of parallax. Okay, if you're not familiar with parallax, don't worry about it. It's 3 1/4 light years, 3.26 light years is a parsec. So the sun's absolute magnitude is about 4.83 if it was about 32 light years away. So that just kind of gets you into, Now, as I mentioned, since the absolute value has a distance factor in it, we can use it very easily to calculate distances. This will all come around here in a minute, okay? There's the formula in case you're interested in it, okay? Distance in parsecs is 10 raised to the visual magnitude minus the absolute magnitude plus 5 divided by 5. Okay? Sure. That's not your thing, don't worry about it, but I just wanted to show you we have an app for that, okay? Yeah. I tell my students, we have an app for that, okay? If you take a star or any hot body and you measure how much energy it's giving off at different wavelengths and graph it, you get what's called the black body curve. That's what you're looking at here, okay? And so here's the visible part of the spectrum. And so if you have a really bright star, a really hot star rather, where it crosses the visible part of the spectrum, there's more blue light than red light, so that star is going to appear blue to us. If you have a much cooler star, where it crosses the visible part of the spectrum, you have more red light than blue light, so that star is going to appear red to us. And then the sun kind of has an equal distribution there, so it's going to appear white, actually a little on the greenish yellow side, okay? There's a reason, as you can appreciate, why our eyes evolved to see that part of the spectrum. If we lived by that star, we would have evolved to have seen that part of the spectrum. So we have some rules for that. It's called black body radiation. And so the first rule is hotter objects emit more total radiation per unit surface area. So that's the Stefan-Boltzmann law. We have an app for that. Okay, there it is. It's a little simpler than the last one. Okay, and this is the temperature in degrees Kelvin. We'll talk about degrees Kelvin here in a minute. But what the takeaway on that, of course, is anything that's above absolute zero is radiating. You're all radiating in the infrared. Okay, you've seen those infrared images of, the police trying to find some convict wandering through the woods, and you can, that's what's going on. That's the Stefan-Boltzmann constant, just in case you were just dying to know what that was. Okay? And then the other one is Wien's law, and that's hotter objects emit bluer photons with a higher average energy. That makes sense. This thing is just not staying up here. That makes sense because the more energy you put into something, you would expect the photons coming off of it to have higher energy. And so that's what Wien's law is stating, and we have an app for that. All right, where the lambda max, lambda is our designation, it's the Greek letter lambda. We use that to designate wavelength, okay? Is that number right there divided by the temperature in degrees Kelvin again. So if we go back to that, that lambda max refers to this peak. So if you can measure the peak, you can measure the temperature on something. Very easily, that's how those no-touch thermometers work. Actually, what they're doing is taking two, I'll show you that on the B minus V here in a minute. But that's essentially how those no-touch thermometers work. You've all looked at Alberio, right? Everybody's favorite double star out there. Okay, one of them is 13,000, so that's going to be more along the blue side here. And the other one's 4,100, so it's going to be kind of yellowish or orangish. And I think you've all probably seen that in a telescope, so you know what I'm talking about here. If you remember from your high school chemistry, hot part of the flame is the blue part of the flame, okay?
Benson honeydew?
Yeah, Dr. Benson honeydew, you got it. Another way to determine temperature, I just love it. We've got, we have degrees Kelvin, you'll see we have B minus V, and we have spectral class. All of those refer to temperature. So another way to determine the temperature is something called B minus V, which is a blue minus visual magnitude. And so what you do is you take a measurement of the magnitude of a star with a blue filter and then a visual filter, and you notice there's a difference between those two. And it turns out the difference between those two correlates to temperature. Got a B minus V of minus 0.4 or minus 1, that correlates to temperature. In fact, that's the way we take the temperature of things. There's other ways we can do it too by looking at certain spectral lines, and I won't go into all that, okay? And there's the app for it, yay! A really good one, okay? So that's the app for the B minus V. So that measures temperature just like Wien's law does. In fact, that's how those no-touch thermometers work. They're looking at 2 points on the graph, and they're looking at the slope and calculating the temperature from that. So it's much easier to obtain. You only require 2 measurements. So kind of putting this whole thing together, if you remember anything about the spectrum, you get this nice continuous spectrum from a hot body, but if you give it a glowing gas cloud like the atmosphere around a star, it creates these dark lines, which you can use to analyze it and figure out what it's made out of. And then if you have a glowing gas cloud, you're going to get these bright lines. Those correspond to these. These all correspond to each other. So you can actually figure out what something's made out of. And of course, all the various atoms, everything all have their own unique signature, okay, or spectral group of spectral lines. The other thing that happens that you're probably familiar with is the Doppler effect. As an object is moving towards you, the light waves are scrunched together. Shorter wavelengths are blue, so we call that blue shift. If it's moving away from you, the light waves are stretched out. Longer wavelengths are redder, and so we call that a red shift. And that's just sort of an example of it. Well, back in the late 1800s, and some of you may remember the talk I gave a number of years ago about the Harvard computers, dry plate photography was invented, and we understood the spectrum for the first time in the late 1800s. And so those two got combined at Harvard University under Edward Pickering, and he hired a whole group of women to analyze these photographs. They were taking photographs of spectra, and it was a time when we actually moved astronomy from sitting in a telescope, we moved it into the lab. And Wilhelmina Fleming was one of their primary people on that. And they started classifying stars based on the strength of their hydrogen lines. And they classified them A, B, C, D, on down the line based on the strength of their hydrogen lines. These are the various computers she had. Okay, they called them computers. Okay, it's an interactive computer system. Okay, they all worked in the same place. Anyway, enter Annie John Cannon. Annie John Cannon was one of the Harvard computers, but she realized that temperature was much more important than the strength of the hydrogen lines. So they rearranged everything. She kept the initial designations and rearranged things according to temperature. And that's why we get this jumbled up letter sequence from the hottest to the coldest of OBAFGKM, which the way to remember it is what I refer to as the astronomer's pickup line, which is, oh, be a fine girl / guy, kiss me, okay? And so that's the hottest stars are the O types, the coolest stars are the M's. The sun is a G2 star, all right? So we further refined it and we broke these down into 10 subcategories, 0 through 9. And of course I said the sun is a G2 star at 5,800 degrees. So now we have 3 ways to talk about temperature, just to confuse everybody. And surprisingly, the temperature matches up with the colors, as you see here. They're not as pure as that, as you're all probably aware. So this sort of puts the whole thing together real quick, just to get you everybody oriented now. You've got spectral class across the top here, OBFGKM. You've got temperature just underneath there. And you have color, B minus V, down there. They're all correlated. So you're going to see, I brought that up because you're going to see slides here that some of them have B minus V, some of them have spectral class, some of them have temperature. Well, a big thing that was going on in the late 1800s, early 1900s, was measuring double stars. In fact, if any telescope that was worth anything came along with what's called a filar micrometer for doing these measurements. I own a 5-inch Alvin Clark refractor, which is a really cool telescope, okay? Made by Alvin Clark in 1873, and it has a filar micrometer with it. Okay, and it was for measuring double stars, okay? About half the stars in the night sky are multiple stars, as I tell everybody. When you make a star, you got leftover stuff. If you got enough leftover stuff, you make another star. If you don't have enough leftover stuff, you make planets. So we're living on the leftover stuff for making the sun, okay? So some of them you can see, those are visual binaries. I'm sure you all have your favorites. In fact, I think a couple of years ago, I did a talk just all on double stars. Some of them you can tell from their spectrum, and some of them actually eclipse each other. They pass, when they're orbiting, they pass in front of each other. And we'll talk about each one of those. So visual doubles, those are the ones you can actually see in a telescope. And if you measure their orbits, which is what a filar micrometer is all about, you can calculate their masses. It's the only way we can calculate a mass, okay, is by having 2 stars or something orbiting something else. That's why Venus, for example, until we sent spacecraft and looked at the deflection from the gravity of Venus, we were never absolutely sure of the mass of Venus. We could estimate it because we're pretty much sure it was about as dense as the Earth, but that was just a guess. The same game with Mercury, but all the other planets have got moons orbiting them, so you could calculate their masses. Pretty straightforward. So it turns out that these guys orbit about a common center of mass, okay, like that. In fact, the Earth-Moon system, we always say the moon orbits the Earth. Not really. They're both orbiting about a common center of mass, which is about 3,000 miles off the center. Okay, so the Earth is wobbling around back and forth just from the moon. And so what we have here is we've got a couple of stars, and they're orbiting about this common center of mass. And it turns out that the ratio of these 2 radii, okay, this one and you know, this one and this one is inverse of the mass. Well, we got two unknowns and only one equation, so you know from your high school algebra that you can't solve that yet. So let's throw that up there, okay? One more biggie. You might recognize this if you just ignore that for a minute as Kepler's second law of motion, the planetary motion. And this is Newton's modification to it, which gives, this is the period, and this is the radius of the orbit here. And if you square that, cube that, plug everything in there, you can figure out what the masses are. Because you got two equations, two unknowns, and you all know again from your high school algebra that you can solve that. And so that's how we're able to calculate the mass of the stars. Otherwise, we wouldn't be able to do that. Okay, so we've got three properties of a star we can measure. We've got luminosity, which is the wattage on the light bulb, if you want to think about that. Okay, that's done in watts, solar units, absolute magnitude. Okay, any one of them worth. Then you have surface temperature, which is in degrees Kelvin, which is spectral class, or B minus V. And we got the mass. We only have one thing for the mass. So it's a little bit easier that way, okay? It turns out that these first two, surface temperature and luminosity, were critical in figuring out what's going on with a star. Turns out that if you plot luminosity versus mass, notice everything's falling in a straight line here. There's the formula for it again, in case you're so math inclined. So knowing the luminosity, we have a very interesting correlation with the mass. Somehow they are related. Now we get to the heart of the talk here. Okay, Hertzsprung-Russell. Okay, these two guys. In 1910, Hans Rosenberg actually published the apparent magnitude of the Pleiades cluster. Okay, and he plotted it against the strength of the calcium K line, which is actually kind of a stand-in for temperature. Okay, as the temperature changes, so does the strength of that calcium K line. So you can use it as another measure of temperature. And that's what he got. So it turns out for a cluster, you don't need to know the luminosity. Because remember, luminosity and brightness are related by the distance. And since for a cluster, the distances are all the same, then luminosity and brightness are essentially interchangeable, at least for graphing purposes. So shortly afterwards, Danish astronomer Hertzsprung created a diagram. It was an absolute magnitude versus color. Okay, so we're kind of getting there. And a year or so later, Russell did one, same relationship, however, he used spectral class rather than temperature. And the net result is this guy. This is the HR diagram. It's a plot, like I said, of luminosity versus temperature. But the interesting thing about it is, so this is just the opposite. The temperature decreases as you go to the right. Call it what you will, Holy Grail, the Rosetta Stone, but this is the graph to understand stellar evolution and what's going on. So first thing you notice, all the stars are pretty much in a line. Okay, we call that the main sequence. There are some outliers up here, down here. We'll talk about those later. Okay. So notice that the mass is on here also. And notice the mass is increasing with the increase in temperature. So we're maintaining that mass-temperature relationship and luminosity. Knowing the star's mass, you know how long it's going to live and how it's going to die. Everything in a star's life is predetermined at birth by by its mass. Okay, it's basically its DNA, okay? So these are the life expectancies. Don't confuse these with age. This is not age, you know. I usually tell my students, you know, the average life expectancy of everyone in this room is about 80 years old, and I'm the only one that's close to that. Well, looking around and saying, I can't say that anymore. Okay. But you get the idea, right? It's life expectancy. So the stars up here, they live fast, die young, okay? About 10 million years. These guys are about 100 million years. A star like Sirius, about 1 billion years. As far as its life expectancy, the sun, 10 billion years. We're about halfway through it. So we're in good shape there. Stars down here have life expectancies of over 100 billion years. So stars down here that were formed at the beginning of the universe are still around, okay? Because they have life expectancies that are beyond the age of the universe is right now. So there is this mass-life relationship. And it depends really how fast the fuel is being burned. More massive stars have a lot more mass, but they're burning it at a much, much faster rate because they're the hot blue stars. Okay, the cool stars are just sort of, you know, chugging along, burning their hydrogen very, very slowly. So the available fuel, like I said, is essentially proportional to the mass. And because of the higher temperatures, it's burning it much faster. And we have an app for that. Okay, there it is. So the length of the life expectancy of a star compared to the sun is the mass of that star compared to the mass of the sun raised to the 3.5 power. And that'll give you the life expectancy. So can plug all this stuff in. I'm not going to go through the math stuff. I just wanted to show you that there's math behind all of this. Okay? So if we know a star's temperature and it's on the main sequence, we know its luminosity. Okay, so if you know the star's temperature and it's on the main sequence, and you can tell it's on the main sequence. I didn't think I thought I had a slide for this, but apparently I don't. Talk about stars, for the most part of their lives, are going to be on the main sequence and they're burning hydrogen in their cores. Okay? So the sun, for example, is burning hydrogen in its core, converting hydrogen to helium. So that's what's happening to all these stars. So you can look at the spectrum and you can kind of tell where a star is in its life cycle. So if you know what its temperature is, you can read its luminosity across there. All right? And if you know its luminosity, you can measure its brightness and figure out its distance. This is the way we did this before we sent up these couple of spacecraft, primarily Gaia. Okay, it's called spectroscopic parallax, and it's a way to calculate the distance to a star. So if a star is on the main sequence, okay, and we observe its parent's magnitude as m, and we can figure out its absolute magnitude from the HR diagram, then there's that formula again, the distance in parsecs. M minus m, you know, the difference between the m's plus 5, take that total, divide it by 5, and take 10 and raise it to that power. It'll give you the distance in parsecs. It's amazing how cool that works, by the way. If you got an HR diagram, okay, and you find a star that you can look up and find its distance and actually calculate it yourself, you'd be surprised how close you come. Okay? So let's take a star that we find it's an F2, has an absolute magnitude of plus 0.4. Okay, so you're looking at that there. And we measure it at a 9.5 magnitude, relatively dim star, and you know, decent telescope to see it. And you can plug it all in, you got to find out it's 126 parsecs away. So that's one of the uses of the HR diagram. If you know the luminosity, and the temperature, you can figure out its size. Okay, if we go from the Stefan-Boltzmann law, if y'all remember back about 6 slides ago, okay, or about 10 slides ago, the Stefan-Boltzmann law, the total luminosity is going to be the surface area multiplied by the amount of energy per square meter. And you get the energy per square meter from the Stefan-Boltzmann law. Back there. Okay, this is the surface area of a sphere. There's the Stefan-Boltzmann law. That'll give you the luminosity. Well, you've measured the luminosity. And the temperature. The only thing you don't know is its radius. So you can calculate its radius. You rearrange stuff and you get that guy. So if you know a star's luminosity and temperature, you know how big it is. Again, this is for stars on the main sequence, not stars off the main sequence. One of the other things we can do with the HR diagram is studying clusters. You've all seen star clusters, right? Globular clusters and open clusters. Of course, globular clusters are, these are these spherical things that are in a halo around the galaxy. Typically have about 500,000 stars in them. Okay, they're pretty bright. They're outside of the Milky Way, so they're away from all that dust and stuff. All right. Open clusters are inside the galaxy, and they're smaller groups, a couple hundred stars. Stars are born in groups. We were part of an open cluster at one time. I like to tell everybody we got kicked out because we didn't play well with others. But it turns out it's the gravitational forces of the galaxy that ripped us out of there. And that's why we're floating along. So these guys are inside the galaxy, and again, they contain several hundred stars. Clusters are really handy. We've got professional astronomers who spend their entire career just studying clusters. And why do we really, really like to study clusters? Well, they're basically made from the same stuff. Okay, so their composition is about the same because they came out of the same gas cloud. So that takes one of the variables out of all the analysis. They're all about the same age. Okay, give or take a couple million years. And in a lifetime of a star, a couple million years is no big deal. Okay? They're all about the same distance. It takes that whole distance luminosity thing right out of it. So that's really handy. And if we plot an HR diagram of just the stars that are in a particular cluster, we can figure out how old that cluster is. Note that this is a plot of a globular cluster. Notice there are no stars up in this area. About 1 solar luminosity, okay? Well, a 1 solar luminosity star lives, remember I told you a while ago? About 10 billion years, okay?
10 billion?
Yeah, about 10 billion, okay? So the sun's gonna live about 10 billion years. So those stars are still around. So we know this, but anything with a life expectancy of less than that has all died off. So we know that this star cluster is about 10 billion years old, just from that. Turns out it's about 13 billion years. Universe is 13.7. So globular clusters are the oldest objects in the universe. Think about that next time you're looking at M13, okay? These are some of the oldest objects in the universe. By the way, we kind of know how they form, but we don't know why they form because we see them around other galaxies. So if anybody's looking for a PhD thesis, okay? That'd be a good one. All right. So here's kind of a way, if you didn't quite follow me there, here's another way to think about it. Think about an orchard somewhere that somebody planted, and there's different trees of different life expectancies, okay, of 5, 10, 15, and Yeah, 5, 10, 15, 20, and 25 years. Now, I know trees live longer than that, but play along, okay? You don't know when they planted it, but you know they planted it about the same time. So you know all these trees are about the same age. And this is what you see when you're looking at this orchard. Oops. You don't see any trees with a life expectancy of 5 to 10 years. They've all died off. What does that tell you? That tells you that this orchard is at least 10 years old. But there's some 15-year-old ones around, or 15-year life expectancies around, so you know that it's greater than 10, less than 15. I don't know if that muddied the waters or made it clear to you, but that's how we can figure out the age of clusters. You're all familiar with the Pleiades cluster. There's its HR diagram. So stars above about 100 solar luminosities now have peeled off the HR diagram, or off the main sequence. So that tells us that the Pleiades cluster is about 100 million years old, because these stars live only about 100 million years. So it's between 75 and 150. And there's other ways we can figure out a cluster's age, but this is the first approximation. And it's actually a pretty good one. Well, some of the other work that was done, particularly by Antonio Morrow at Harvard, had to do with the width of the hydrogen lines. And Antonio Morrow, for some reason, had this insight that the width of the spectral lines was going to be important. So when she found stars with a wider line in the spectrum, she gave it a designation of C, just to set them apart, okay? And Hertzsprung looked at stars that had a narrow line, and he noticed they had smaller proper motions. Proper motion is how much the star is actually moving against the background stars. And solar proper motions indicates they're farther away. It's not a real good estimate of distance, but it's not a bad relative one. So he found out that this is called secular parallax, by the way. So that allowed him to estimate the distances to these stars. And so the greater the distance for the narrow spectral lines gave him some idea of size. All right, and I won't go into the details on that, but it found out that this C designation separated out stars that were off the main sequence of the HR diagram. And one group of stars that's off on the lower left, which we'll talk about in a minute, are the white dwarfs. And the first one was actually discovered as 40 Arandi, okay? And Henry Russell and Edward Pickering and Wilhelmina Fleming discovered it despite the fact that it was a dim star and it was a spectral type A, which is a hot star. Remember, OBA, okay? So it was a really hot star, but it was really low luminosity. And that meant it was a small diameter. And so hence the name white dwarf. So I probably should have had those slides in a different order. Here are these other guys on the HR diagram that are outside the main sequence. So the ones in the upper right, these are called the red giants. They're really big stars. And really cool, by the way. Ones in the lower left are the white dwarfs. Now, rather than compromise the usefulness of this thing, it gave us some real insight into the evolution of stars and what's going on there. Okay? And it was Arthur Eddington that first proposed this, and this was before we knew how stars worked. Okay, we had no idea where they were getting their energy from. We knew it wasn't chemical energy or anything else because they wouldn't last that long. And after Arthur Eddington heard a presentation by Russell in 1912, he came up with this basic idea. He wrote a textbook on the internal constitution of stars. And he anticipated nuclear fusion and correctly proposed that the star's source of power was going to be this combination of hydrogen and helium. And again, this was a huge jump in insight because we didn't know anything about nuclear fusion. Okay. And also, we didn't know if the stars were primarily hydrogen. That was actually determined by Cecilia Payne. She was using the data, again, from the Harvard computers, and she was the one that determined that hydrogen was the overwhelming constituent of the stars. This was a heck of an insight at the time. We were not, we didn't really understand what they were totally made out of. So it was Hans Bethe that discovered that nuclear fusion was the possible energy for the stars, which made everything kind of work. Oops. So here's what's going on. We've got really high temperatures and really high pressures in the center of stars. And so with the really high pressures, we're trying to push these protons together because there's a lot of loose protons flying all over the place. And they're moving really quick, so they want to smack into each other. And of course, they're both positively charged, so they repel each other. It's like trying to push two like poles of a magnet together. The closer you get them, the harder it is to push them together. And it turns out that if you get them close enough, and I mean really close enough, then the nuclear forces take over. Nuclear forces work over very, very short distances. And the nuclear forces take over, and it overcomes this repulsion from the electrical forces, and the things stick together. So here's what's going on inside of a star. We've got hydrogen, we smack two of them together, we get a deuterium, and we get a positron and a neutrino, but you get some gamma rays off. That's the energy that's generated there. And then if you smack another hydrogen into it, you get a helium-3. If you smack two helium-3s together, you get a helium-4, which is the stable one that's on the periodic table, and you get two of the hydrogens back. So if you total this thing up, you got 1, 2, 3, 4, 5, 6 hydrogens, you get 2 back, so it took 4 hydrogens to make 1 helium. That's what's happening. And with each one of these reactions, you get some energy off, and that's where the energy is coming from the star. And a main sequence star, we call this burning, it really isn't, it's a totally misnomer, okay? But we call it burning, and so we're burning hydrogen to make helium. And so it's called a proton-proton chain, just in case. Well, it turns out if you weigh the 4 hydrogens and the helium, the 4 hydrogens weigh more than the helium does. How did that happen? Okay, remember the total should be this, equal to the sum of the parts. Well, it is sort of. The difference is the conversion of mass by that formula right there. Everybody's seen that? That's Einstein's conversion of mass. So the energy release is that difference in mass times the speed of light squared. Speed of light is a big number. You square it, it's a really big number. Okay? And so it doesn't take a lot of mass to convert it into energy to create a lot of energy. So the star's got this balancing act. Right? In the core, there's all these hydrogen bombs, literally, going off on the inside, trying to blow this star apart, but gravity is holding it together. And so it's this balancing act. It's called hydrostatic equilibrium, and it's self-regulating. What is kind of neat here is that the star expands and the pressure in the core drops. the rate of fusion drops. And so there's not as much energy trying to blow the star apart, so it wants to shrink back down. If it shrinks back down too much, as you compress it, you get more and more energy release, and that starts to blow it apart. So it gets this nice stable spot, okay? So these outlier stars are stars in different stages of their evolutionary process. So as hydrogen is burned to create helium, that causes some of the other properties to change and stuff, and I'm not going to go into that too much. But let's take the evolutionary track of one solar mass star. Sun's going to do this, okay? What's going to happen eventually, it's going to run out of hydrogen in the core. And the core is going to collapse. And when you compress a gas, remember PV is equal to nRT from your high school chemistry? Okay, when you compress that gas, it's going to increase in temperature. And that's going to allow fusion in the shell around the core. And there's a lot more hydrogen in the shell, so there's a lot more energy released. And so that forces the star to blow up, or to expand. I won't say blow up, because that's a misnomer. To expand, and it'll become a red giant, because as those outer layers expand, they're going to cool. And when they cool, remember the cooler stars are redder stars. So they become a red giant. Eventually, the helium in the core starts to burn. This all happens, by the way, pretty quickly. All right? And pushes it out even more. In fact, the sun is going to get so big that it's going to engulf Mercury, Venus, and we think possibly the Earth. That's how big it's going to be. Betelgeuse is a red giant. You all know about Betelgeuse. You look at Orion, it's in the upper left. And hopefully you've noticed that it's red. If you haven't, compare it to Rigel. Rigel is the star diagonally across from it. And if you look between those two very quickly, all of a sudden it becomes very obvious that Betelgeuse is red and Rigel is blue. Okay? So try that next time you're out looking. All right? So this whole additional energy being generated inside the star boils off the outer atmosphere. And we see that as a planetary nebula. Okay, the Ring Nebula, that's a star and dying, M27, the Dumbbell Nebula. All those are dying stars. And what's left in the core is a white dwarf. So this poor guy has been through its entire life cycle. And so, there's M27 and M57. High mass stars go through a much higher rate of burning. And so they go through more cycles. So they not only fuse hydrogen into helium, but they also fuse helium into carbon and oxygen and all this other stuff. The end of the line is iron, okay? Once you get iron in the core, if you try to fuse iron, it takes more energy to fuse it than you get back. And so you actually are doing everything in reverse now, and the core is getting cooler very quickly, and the whole thing wants to collapse. And it collapses violently. Just whoom, kabam, and blows apart. And that's where supernovas come from. Probably all seen the Crab Nebula. Very disappointing, by the way, in a telescope. Never looks like this. Okay. Just kind of this fuzzy blob. There it is. Okay. So low mass stars, they lead a long, quiet life. Okay. As I said, some of them have life expectancies past the age of the universe. That's because they burn their hydrogen much more slowly, and when they die, they leave this puff of gas and retire as a white dwarf. High mass stars live fast, die young. Okay? Kind of like our brightest Hollywood stars. Okay? Great comparison. Okay? They're all leading these fast lives, and they die pretty quickly because they're burning their hydrogen much more quickly. And so when they leave, though, they leave in this blaze of glory. Okay? Just blow up. So stars arrive on the main sequence. It's a rather short period, okay, for them to arrive on the main sequence because the stars collapse from a gas cloud. And once fusion starts on the inside, they wind up in a certain spot on the HR diagram. And that's where they spend most of their lives, okay, in one particular spot on the main sequence on the HR diagram. So the mass of a protostar tells you how long it's going to take to get there, okay? And what's interesting is these guys get there in a hurry, okay? These guys take a little longer. Now, 150 million years, by the way, is not a big time, you know, when you start talking about billions of years for the age of a star. So that's how they arrive on the main sequence. So the upper limit is about 100 solar masses. Lower limit's about 0.08 solar masses. Jupiter is less than that. If Jupiter was about 80 times bigger, it would be a star. It would turn into a star. Okay, some more things that were going on with the HR diagram. In the 1930s, Morgan and Keenan at Yerkes Observatory developed incorporated luminosity classes, and they labeled them with Roman numerals, okay? And again, that was based on the width of their spectral lines, that C designation that Antonio Mauro came up with. And they correspond to these diagonal bands here. So these are V's, or a 5, okay? That's the lumina. A 4 is a subgiant, a 3 is a giant, a 2 is a bright giant, and then there's 1A's and 1B's. Those are the luminous and less luminous supergiants. So, well, okay, so a 5 is a main sequence star. And then not shown on here are the 6s and 7s, which are the dwarfs and the subdwarfs. So to get a complete classification of a star, you need its spectral class plus its luminosity class. If you know those two, you know exactly where it's sitting on the HR diagram. So the sun is a G2-5, in Roman numeral 5. And that tells you that it's on the main sequence. Betelgeuse is a M21b, okay? So I'm sure if you look up any information on a star, you're going to see these kind of designations, so you know what they mean.
Question?
Yeah.
So with the spectral line, is that telling you the proportion of hydrogen and helium? Is that why?
No, it's giving you the size of the star.
Oh, okay.
All right. It actually correlates to the size of the star because of the rotation.
Okay.
So the size of the stars, you can actually calculate, and it turns out it follows these diagonal straight lines right along here, okay? So that increases you increase the radius. This is 1,000th the radius of the sun. Here's a 1, obviously, for the sun. This is 10 times the radius of the sun. So if you know where a star is on the HR diagram, you know a lot about it. You know its mass, you know its luminosity, you know how long it's going to live, and you know its size. Basically, you know everything about it. Now, there is one little section here on there called the instability strip. There are times in a star's life when they're unstable. When they're young and when they're old. Kind of like people that way. All right? And so they vary in brightness. And, well, varying luminosity is what they're doing. And it turns out that there's a spot where they pretty much all live, and there's Cepheid variables, RR Lyrae. I won't talk about variable stars, that's a whole other lecture, okay? But they found a spot on the HR diagram also. So if you put it all together, you got stars coming in this way, showing up on the HR diagram in various places. And as these last stars are getting involved, there's these guys on the top are peeling off, okay? And then eventually you get everybody on board, and then these stars just continually peel off, is what's happening, you know, over time. So that's pretty much it. Whoops. Okay. So what you've got is here's the diameters. These are the luminosity classes aren't shown on there. But you know what the diameters are. Okay, quick word, that's my observatory at BW. Really neat place. We do have open houses there twice a semester. We've already had one this year. But the next one is Don Driscoll from Kent State. He teaches one of the sections, the most popular course on campus, which is the 7 ideas, a survey of the great ideas in science. And so he's going to be talking about this. It's just not astronomy this time. It's, you know, a whole raft of things. So it should be fun. All right, well, I'll try and answer any questions if anybody's got them. Okay? Yes?
Early on in your presentation, you mentioned some mass between the sun, the Earth, and the Moon that was affecting the orbit somehow. Did I hear that right? If so, what was that?
Well, no, what I'm saying is that the Earth and the Moon orbit about a common center of mass, like these two here.
But what is the center of mass? Where is that?
Okay, center of mass is the exact balance point between these two.
Okay.
All right? And so the Moon and the Earth, the balance point is about 3,000 miles from the center towards the Moon.
That's right.
And so the Moon or the Earth is wobbling back and forth like this just from the Moon orbiting. That's what creates the tides on the opposite side. We got 2 tides, okay? Got another lecture on that, but it turns out that the Moon, because of the Earth's rotation and the tides, is actually getting pushed further away. And so it's moving out at about 4 meters a century. It's moving out further, and the Earth is slowing down because of that. So we're slowing down about 1 second a century, about a half a second a century. So 350 million years ago, the day was 23 hours long. Okay? Anybody else? Did I lose everybody?
Would there be like a good book or text that would integrate all this stuff?
Most introductory textbooks will do that. If you look at Kaufman's The Universe,
Okay.
that's a college textbook. It's about that thick. But, you know, he goes through the HR diagram, but he also goes through an awful lot of the background. I just went through I just basically touched on it.
So it's Kaufman's The Universe?
Yeah. Anybody else?
So in terms of the new database like Gaia,
Yes.
how Hertzsprung-Russell Diagram stands in terms of categorizing 20 million stars?
Right. What that does, it gives us a chance to put a finer point on this, okay? Most of the distances were reasonable, okay? But the Gaia spacecraft, I mean, it nailed these things down to like inches. Not quite inches, but it really it narrowed a lot of stuff out. It really took the error bars and really scrunched stuff down, so.
We have some subclasses in each class, for example, white dwarfs, different types of white dwarfs, or something like that.
What's that?
So the classes that we know classically, do we have a subclass of that? For example,
Subclasses of,
Oh, yeah, there's some classes of white dwarfs.
right, so I think Gaia had, what, 30,000 white dwarfs in there?
Oh, at least I don't know what the numbers are, but they,
So I was wondering, there's some,
Right. They're still analyzing data because Gaia was just, that data was just released a couple of years ago. So they're still going through and analyzing all of that. And so it's going to be interesting. For those that are not familiar, Gaia was a spacecraft launched by the European Space Agency, and it measured the distance to 200 million stars.
20 million.
Yeah, something like 200 million stars to an amazing precision.
So it was
It's
actually,
not inches, but it's close to it. I mean, it really is a phenomenal piece of equipment. But they finally decommissioned it, and the data has been published, and there are people going through it like crazy trying to figure this out.
so Gaia was measuring what, brightness and color, was exactly measuring?
Yeah, actually, they were measuring parallax, okay? Because it was in orbit around the sun. Now, I don't know how they got the precision they did, okay? I'm probably going to wind up doing a lecture on Gaia just to learn that, okay? But it's an amazing piece of equipment. I keep hoping to try to find somebody that was an expert here in the U.S. so they could talk to the Cleveland Astronomical Society about it, because it really is an amazing piece of work.
let us know if you get that expert, because I want to be in that lecture.
One of the neat things is some of the large stars, it couldn't measure the distances because the star was so big. Like Betelgeuse, they couldn't measure a distance to Betelgeuse because Betelgeuse has got some size to it. So yeah, it's that precise. It's a phenomenal piece of equipment. Okay, guys, well, I thank you all for your attention. Would have gone better had I had my slide advancer because I'm, trying to think of what. Okay.